You are transferring 500 euros to a friend. Step 1. Deduct 500 euros from your account. Done. Step 2. Add 500 euros to their account. Server crashes. Step 2 never runs. 500 euros has left your account. It arrived nowhere. Not stolen, just gone. In a distributed system with no transaction guarantees, this is not theoretical. It happens. Today we are going deep on the mechanism that makes this impossible, database transactions. And we are not just covering the surface, we are going all the way down to how Postgres handles this under the hood. Let's go. What is a database transaction? A database transaction is a sequence of operations, reads and writes, that are treated as a single unit of work. The rule is simple and obsolete. Either all of them succeed or none of them happen. There is no partial success. There is no 3 out of 4 completed. It's all or it's nothing. In SQL, you explicitly control this. Here's the code to commit or roll back. The commit happens if everything goes well. If something goes wrong, everything gets rolled back. Every modern relational database like Postgres, MySQL, Oracle, SQL Server supports this model. The guarantees it provides are described by 4 properties you need to memorize. They spell ACID, Atomicity, all or nothing. The A in ACID is atomicity. Atomic means indivisible. In chemistry, an atom was thought to be the smallest unit that couldn't be split. In databases, an atomic transaction can't be split. It either executes completely or it doesn't execute at all. If your server crashes, power fails, or a constraint is violated mid-transaction, the database rolls back every change that had already happened within that transaction. That database is left exactly as it was before you began. The 500 euros stays in account A. Account B gets nothing. No data is corrupted. It's as if the transaction never happened. How does this work mechanically? The database keeps an undo log, a record of the old values before each change. If it needs to roll back, it reads the undo log in reverse and restores every original value. The C in ACID is consistency. A transaction can only move the database from one valid state to another valid state. Valid here means your application's defined rules and constraints are satisfied before the transaction and after the transaction. Examples: a bank account balance can't go below 0 if you have a not null constraint. A foreign key can't reference a row that doesn't exist. A unique constraint can't be violated. If a transaction would leave the database in an invalid state, the database rejects it and rolls it back. Importantly, consistency is one ACID property that isn't purely the database's job. It's partly the developer's job. The database enforces constraint, but if you write a transaction that doesn't enforce your business rules correctly, the database doesn't know your business rules. You have to encode them as constraints. Consistency is the contract between the developer and the database. The database enforces what you tell it to enforce. The I in ACID is isolation. This is where it gets genuinely complex. And this is where most engineers don't go deep enough. Isolation means concurrent transactions must not interfere with each other. If 2 transactions are running at the same time, each should behave as if it's the only transaction in the world. Without isolation, you get 3 classic problems. Number 1, dirty read. Transaction A updates a row but hasn't committed yet. Transaction B reads that row. Transaction A then rolls back. Transaction B has read data that never officially existed. Number 2, non-repeatable read. Transaction A reads a row. Transaction B updates and commits that same row. Transaction A reads that row again and gets a different value. The same query returns different results within the same transaction. Number 3, phantom read. Transaction A queries for all orders over 100 euros. Transaction B inserts a new order over 100 euros and commits. Transaction A queries again and gets a different set of rows. Rows appeared phantoms. These problems exist because for performance, databases allow concurrent transactions. Full serial execution. One transaction completes, then the next begins, is perfectly safe but destroys throughput. The solution is isolation levels, a configurable trade-off between safety and performance. The D in ACID is durability. Once a transaction commits, it is permanent. Even if the server loses power 1 millisecond after your commit returns, that transaction is not lost. This is an absolute guarantee. How? The write-ahead log. Here's how it works. Before the database writes changes to its actual data files, it writes a description of those changes to the val, a sequential append-only log file on disk. The val entry is written as flush to disk before the commit is acknowledged to the client. So when your application receives commit successful, the val is already on disk. The val is also the foundation of replication. Read replicas receive the val stream from the primary and apply the same changes in the same order. This is called streaming replication. The val is the single most important file in your database. Protect it, back it up. It's the source of truth for everything that has ever happened. Where does all this appear in systems you use every day? Stripe. Every payment uses a transaction. Charge the card, create the payment record, update the account balance, all in one atomic transaction. If the card charge succeeds but the record creation fails, the transaction rolls back and the charge is reversed. Flight booking systems. Checking a seat is available and reserving it are done inside a single transaction, which select for update, locking the seat row so no other transaction can reserve it simultaneously. E-commerce. Deduct inventory, create order, create shipment, all atomic. If the shipment service is down, the order doesn't exist and the inventory isn't deducted. The pattern is the same everywhere. Any operation that involves more than one step and must be consistent uses a transaction. Let's land this. Atomicity, all or nothing. The undo log makes rollback possible. Consistency, valid state to valid state. Your constraints define what valid means. Isolation, concurrent transactions don't see each other's in-progress work. Isolation levels are the knob between safety and performance. Durability, committed means permanent. The val is how the database survives crashes. If you found this useful, subscribe. Next video we are going inside fraud detection systems. How your bank blocks a fraudulent card transaction in under 100 milliseconds without a single human reviewing it. ACID isn't just a database concept, it's a design philosophy. Guarantee your invariants or don't promise them at all.